are equivalent circuits. Instead of the electricity that often necessary to produce the complex circuit into a simpler form, any of the complex circuits considering resistance can be drawn with the reduced to basic equivalent circuit containing the voltage source. A single resistor representing total resistance process is called also reduction of the equivalent circuit. Figure 3049 show the parallel circuit with the three resistors equal value. Redrawn equivalent circle. The parallel circuit is shown in Part A. Show the original circuit to create the equivalent circuit. It must be first calculated the equivalent resistance. So you have 100 volts, 45 volts, 45 volts. That'd be 100 volts at 45 ohms for resistor 1, 2, and 3. 100 volts at resistor required 15 resistor. B parallel circuit of resistor 1 45 ohms, resistor 2 45 ohms, resistor 3 45 so you take the resistance 45 over the number 3, which gives you 15 ohms of the resistance equivalent. Once the equivalent resistance is known, the new circuit drawn and consisting of a single resistor to the representing equivalent resistor voltage source. Okay, so Alright, continuing. Rules of parallel DC circuit. The same voltage exists across each branch of the parallel circuit and is equal to the source of the voltage. The current through the branch of the parallel net is inversely proportional with the amount of the resistance of the branch. The total current of the parallel circuit is equal to the sum of the individual branch currents of the circuit. The total resistance of the parallel circuit is found with the general formula. The resistance equation is equal to 1 over R, or 1 over the resistance equation R1 plus R2 plus to the R numerical, or one formula derived with the general formula. The total power consumed with the parallel circuit is equal to the sum of the power consumptions of the individual resistance. Solving a parallel circuit problem. The problems involve the determination of resistance, voltage, current with the power of the parallel circuit. The solve of the simply of the series circuit with the procedure for the same with the one drawing the circuit of two. Say the value of the given the value found, and select the equation to be used for the solving with the unknown quantity based upon the known quantity. Substitute with the known value of the equation you have selected to solve the unknown value. Parallel circuit shown in the 5 resistors. Each value of each of the resistors is known. That the current resistor 1 is known. That you ask and calculate the value of the total resistance, total power, total the current source of voltage power used to each of the resistor. The current of the resistor 2, resistor 3, resistor 4, resistor 5 are given. So resistor 1 through resistor 5, 18, 3, resistor 1 20, resistor 2 30, resistor 3, 18, and resistor 4 18 resistor, and the amperage of resistor 1 is 9 amps. So to find RT, the resistor total, or the voltage ES, the amperage total, the power total, the amperage at resistor 2, resistor 3, resistor 4, and resistor 5, power resistor 1, resistor 2, power resistor 4 and 5. This may appear a large amount of the mathematical manipulation. However, it is used with a step-by-step approach. The circuit will fall apart quite easily. First step in solving the problem is you draw the circuit and indicate the known value for the shown figure 350. So you have the your voltage and your resistor 1 at 20 amps, resistor 2 at 30 resistor 31 at 20 megas, 30 there goes resistor 2, the resistor 3, resistor 4, and resistor 5, 18 omegas. Also, resistor 1 has the amperage of resistor 1 is 9 amps. Alright, the several ways to approach the problem values have been given that you can solve the resistor total. The power used the resistor 1 with the voltage across the resistor 1, which is known to be equal to the source of the voltage across each of the resistor. The resistor total with the power used by the resistor 1 will not have the solving of the other unknown, will not help solving the other known value. The voltage of the resistor 1 is known, the value will keep to calculate the unknown. Therefore, the logical unknown solve the source of the voltage across R1. Resistor 1 is 20 ohms. The amperage of resistor 9 is 9 amps. So you have 9 amps over 20 ohms would give you the total voltage of the resistor 1 RA would be 9 times 20 amps. 20 megas is 180 volts. Now the source of voltage known that you can solve the current in each of the branch. You have 180 volts at ES. And resistors R2, R3, R4, R5, you want to do the resistor total, but exclude resistor 1 since you found the amps for that, would give you the amps at resistor 2 would be equal to 180 volts over the resistor 2 with the 30 ohms, 6 amps. Resistor 3 with the, would be 180 volts over the resistor 3 would be 18 amps, which gives you 10 amps for resistor 10 amps for that. And then resistor 3, 4, and 5 are equal to voltage of the resistor would be 10 amps over 10 amps. Resistor 1 would be given that resistor 20 and 1 is 20, resistor 3 is 30, resistor 3 and 4 and 5 are 18 ohmegas. You would get the equation. The resistor totals are equal to the resistor equation. Equivalents are 9, 6, 10, 10, and 10. 9, 6, 10, and 10 would give you 45 over 185, which is 4 ohmegas total. Alternating method of solving the resistance total may be observation. You can see with the resistance 1, resistor 4, resistor 5 equal ohmic value. Therefore, equivalent resistor can be substituted with 3 resistors in solving the total resistance. So resistance 3, 4, and 5 are 18 ohmegas. Resistor 1, equation 1 is resistor number, resistor over the number of the resistors, which give you 18 ohmegas. It would give you 3 for 6 ohmegas for both the resistor 3, 4, and 5. The circuit is going to be redrawn. Resistor 1 equation placing the resistor of the 3, 4, and 5 is shown. And showing the 180 volts, 220 volts, resistor 20 and 30, and resistor 1 required 6 ohms. First, equivalent parallel circuit. The equivalent resistor can be calculated with the resistor 1 and resistor 2 by using the product over the same formula. Given that resistor 1 and resistor 2 are 30, the resistor equation is 20 times 30 would be 600 over the 50 would give you 12 ohmegas for resistor 1 and resistor 2. Equation 2 shown figure resistor 1 and resistor 2 figure 352. 352 shows the 12 ohmegas, and then required resistor 1 would be 6. Second equivalent parallel circuit. Now left the 2 resistors of the periodic with the sum of the method used to solve the total resistance. You have resistance equation number 1 being and resistor equation would be 12 ohmegas. So resistor total would be equal to the resistor equation, and so the resistor equation would be R1 plus R2 equals R1, 2, R3. So 6 times 12 and divided by 18 would give you 4 ohmegas. They agree with the solution found with the general formula solved with the resistor and parallel circuit which now be redrawn. Figure 353. Total current can be calculated. 128 volts, parallel circuit redrawn, final equivalent, 4 ohmegas, 180 volts. You have 180 volts V4, total ohmegas, which equals the amperage total would be over the volts over the ohms. Resistance would give you 180 over the 4 amps with 45 amps. The solution can be checked using the values already calculated in branch circuits. Our amperage resistor 1, 2, and 3, and 4, and 5 all have resistor 9 would be 1 would be 9, resistor 2 6 amps, and then 3 and 4 and 5 10 amps would be the total of 45 amps. And also now the total current is the next logical step. The total 180 volts over the 45 amps would give you the solution for that would be the power and effect of the 180 volts times 45 amps would give you 8100 or 181 kilowatt hours divided by 1,000. Give the power each of the branch. A total 180 volts. Resistor 9 amps. Resistor 2 6 amps, which give you 45 amps, and the 180 over 180 volts. So once again, your power effect would be power resistor 1 would be equal to 180 volts times resistor 1 9 amps would be 1,620 amps. Resistor 2 10,080 and 1 amps, and resistor 3, 4, and 5 would be 1,800 amps because they are equal in previous calculation total will now be checked. Then you have just checking it out. You also get 181,000 kilowatts after adding all the power of the resistors together. What term identifies a single resistor representing the total resistance complex in a circuit? Total power of the whole series and parallel circuits could be with the formula power total equal to power 1 plus power 2 to the power plus the powers of the numerics, which come the formula of both series and parallel circuit. The circuit consists of 3 resistor connected with a parallel across the voltage. Resistor 1, 40 ohms for resistor 2, 30 ohms for resistor 3, 40 ohms resistor P3 at 360 watts. Solve for resistor total, voltage total, and the amperage resistor 2. And drawing and label the circuit in first. We're not going to draw that or figure it out. But series and parallel DC circuit, with the pre-discussion of the series and parallel DC circuits have been considerably separated with the technical encounter with the consisting of both series and parallel element circuit, the type of the referred to the combination circuit. So from the qualities element of the combination circuit simply matter and applying with the law and rules discussing up to this point. Solving the combination circuit of the problem, the basic technique of solving the DC combination circuit problems is use the equivalent circuit to simplify the complex circuit in a simple circuit containing only one of the load equivalent circuits are substituted on paper for the complex circuit that they represent. The demonstrated the method used to solve the combination circuit with the network shown in figure 354A will be used to calculate the various circuit quantities such as resistance, current, voltage, and power. Our figure A, well, this is broken down into you have 60 volts, and in examples combination circuit would be resistor 2 would be resistor equation for the 20 ohms, and 8 ohms and 12 ohms. So we have add all the ohms together. You have 58, or resistor 2 and 3. Or resistor 2 and 3 are 50 ohms, and also that's a short when they run in their own circuit A between A and B. But they're running on 60 volts, so they would be 20 times 30 would be 600 over 50 would be 12 ohms for the product of the sum for the A to B resistors for the total resistance equation number 1. Now, the equivalent resistance of resistors 2 and 3 has been calculated. The circuit will be drawn in the series of the circuit figure 354B. So you have 364, and the resistor 1 would be 8 amps, and your resistor equation for the number 1, 12 amps, which was given for this short circuit, which first resistor read resistor 1. The resistor equation for the number that we did number 1 would be 12 ohms. So you have a total of 20 ohms required in station 60 would be volts over the ohms, gives you 3 amps, I believe. Of 10 total amps of 3 amps, total voltage is 60 volts. Power total is equal to the voltage times the amperage total. So you had 60 volts times 3 amps. It would be equal to 180 watts. To find the voltage drop, the resistor 1 and resistor 2 and resistor 3 refer to figure 354B resistor 1 equation. Parallel network 323 and parallel network 322 and 33. So the voltage across the parallel circuit is equal to the voltage of the resistor equation 1 will equal the voltage voltage equation for the equation E. Equation 1 will equal the voltage resistor 2 equals the voltage of the resistor 2 is also equal the voltage across resistor 3 equal and voltage across equal the resistor. So you have 3 amperes over the resistor 1, 8 ohms for the resistor equation 12 ohms like we were at. Current through each of the part series are equal to the total current. The voltage of the resistor 1 at amper 1 resistor 1 would be 3 amps at 8 ohms, 24 volts. Remember where the total was 3 volts, and resistor 1 was resistor 1, 8 ohms, 24 volts. Resistor 2 equals E, resistor 2 equation 1. Equation 1 is equal to 3 amps over the resistor equation 1 with 12 ohms. 36 volts for resistor 20, the resistor 2, and resistor 3 found the power used by resistor 1. The voltage of the resistor 1 is 24 volts, and the amps is 3 amps. Power resistor 1 is equal to the voltage resistor 1 times the amp total for the 24 volts or 72 watts at resistor 1. To find the current of the resistor 2 and 3 for the open circuit, original circuit figure 35 354.5A is the equation resistor voltage is E3 and E4 and E2 and E3 found in the previous equation. You have voltage R2 and R3 36 volts, both with resistor 2 at 20 ohms, resistor 2 at 30 ohms. So you have the amp is a resistor 2 at 30 equal to the voltage of 36 over the resistor 2 at 20 ohms, so 36 1.8 amps. Resistor 3 would be 36 volts over the 30 volts over the 1.2 amps to give it the power of resistor 2 and 3 used for the value of the previous calculation. Given the voltage of the resistor 2 is 36 volts, the voltage at A3 of 36 volts, the amps at the 1.8 amps, the amps at 1.26 amps. The solution of the power resistor at resistor 2 that is the voltage of the resistor 2 times the amp is 36 volt to 1.8 amps, 64.8 watts. Point power resistor, the energy voltage at resistor 3 and the amp of the resistor 3 with the 43.2 watts. Alright, now you have solved the unknown quantity with the circuit that you can apply with what you have learned with the series, the parallel, and combination circuit. Important to remember the first look at the circuit from the observation made to determine the type of the circuit, what is known, which we are looking for, the minute spent with the man, to make sure may save you necessary calculation to have completed with all the current voltage of the figure 354 with the complete description open operation with the circuit can be made with the total current of the 3 amp lead with the terminal of the battery flow through 8 ohm resistor and resistor 1. On doing so, the voltage drop the 24 volts across the resistor 1 and at point A 3 amp. The current divides into two current. The total current is 1.8 amp. There is flow for the 2 ohm resistor, 20 ohm resistor. The remaining current with the 1.2 ohm flow with the point down through the 30 ohm resistor with the point B with the current produced the voltage drop of the 36 volts across the 30 ohm resistor. Note that the voltage drop of the 20 and 30 ohm resistors are the same in the total branch. The current figure 1.8 and 1.2 amps combined with the junction B with the total current with 3 amps flows back toward the source of the action of the circuit. It has been completely described with the exemption of the power consumed, which could be described in the various previously computed. It should be pointed out that the combination circuit is not difficult to solve. The key of the solution is known in order in which steps of solutions must be accomplished. Alright, practice circuit problem, figure 355, typical combination circuit to make you understand the technique solving the unknown quantities, solving the solve for resistor, the voltage of resistor 1. Alright, resistor 1 and 2 and 3 add up to 800, so it breaks down into you add these together and you have like quantities. So resistor 1 equation would be 1 and 2. Resistor would equal 400 ohms. And then you have resistor 2 and resistor equation 1 and 3 with the 400 ohms. Next spot would be to take the voltage from resistor equation 1. Resistor equation 2 would be 200 ohms. Is their lowest common 200 ohms. And then then after the 200 ohms, which would be 1.5 amps, 1.5 kilowatts into the equation, 1.2 combination. I think that was right. It's not necessary to solve all the value of the circuit with the component, compute the voltage drop off the resistor of the resistor 1 and voltage resistor. First, the take the determine the value of the given does not provide information to solve the voltage of the resistor 1 directly. The current of the resistor 1 and amp of the resistor 1 is known. The voltage of the resistor 1 can be computed by applying the following formula. Voltage of the resistor 1 is equal to resistor 1 times the amp of the resistor 1. The following steps will be solved with the total resistance of resistor and total of the calculated equivalent. Given the resistor 1 is 300 ohms, resistor 2 is 100 ohms, resistor equation equals 400 ohms. Redraw the circuit shown in figure B. The resistor equation 400 ohms, resistor equation resistor 3 is 400 ohms. Given the number of resistors, you have 2 divided by 400 ohms, which gives you 200 ohms for your total of the resistor total for the equalizing resistor parallels. So you now have 200 ohms at 400 ohms at 200 ohms. Redraw the circuit of the equation 200 ohms with a resistor of 1 kilowatt, 1 kilo omega. The resistor equation show the resistor equation 200 plus the resistor 4 would be 1.2 kilowatts per hour. The total current of the amp, the total is 300 volts. Of the resistor equation 1.2 kilowatt amps of the amperes total is equal to the voltage over the 1.2 kilowatt amps at 250 milliamperes. Solve the voltage drop across the resistance equation that represents the volt drop across the network resistor 1, 2, and 3 of the original circuit. Given the equation of resistor 200 amps over the amps at 250 milliamperes, the equation resistor voltage question resistance equation for 2 is resistor equation 2 times the amp the total of the 200 amps times 250 amps is 50 volts. Since for the current of the resistor equation 1, the resistor equation 1 represents the network of the resistor 1, resistor 2 of the original circuit, since the voltage across each of the branch per parallel circuit is equal to the value across the equivalent resistor representing the circuit, the voltage of the resistant equation 1 and resistant equation 1 or 2 are equal. They get 50 volts, and resistor equation 400 ohms, so you have the amplitude of equation 1 over the voltage of equation 1 over the ohms of equation 1, you have 50 over 400 amps or 125 milliamps. So the voltage draws across the resistor 1 quantity will be asked that since the resistor equation 1 represented the series parent network pair with the resistor 1 and 2, the total current flow over each of the resistor and series of the current of the amperage resistor 1 must equal the amperage in the resistor 1 equation. So when the amperage resistor 1 is 125 milliamperes, resistor 1 is 300 ohms, which gives you the voltage over the equals to amperage times the resistance of resistor 1 300 megohms equal to 37.5 volts. Question 42. Refer to figure 355 of the following resistors where played with the value to indicate that the resistor 1 is equal to 900 megohms. 900 megas of resistor 3 is 1 kilo mega. What is the whole power circle? What is the voltage of resistor 2? Redrawing circuit with clarity. Well, you'll notice the schematic diagrams have been working with it. We'll have some of the parallel circuits shown with the square figure of each of the branches identified. In actual practice, the welding circuit with the more complex schematics rarely laid out with a simple form of the industry. The important to recognize that the circuit is going to be drawn with various ways and various variety of ways. Learning some of the techniques for drawing them in a simplified form. When the circuit is redrawn with clarity, the simple form of the following steps are used. Show the current path of the circuit, label the junctions in the circuit, recognize the points or same potential. Visual rearrangement, sketching or shrinking, connecting wires. Redraw the circuit within two simpler through the stage and necessary. To redraw any circuit that starts with the source that trace the path of the current flow through the circuit at the point where the current divides the junction parallel branches begin with the junctions or points referenced in any of the circuit that should be labeled. You'll find the wire circuit schematics are assuming no resistance and no voltage drop along the wire. This means that any unbroken wire in the same voltage along its length until then interrupted by the resistor battery or some other circuit component. In the redrawing circuit of the wire with the sketch and shrunk as a mass as much as you like without changing the electrical characteristics of the circuit. Figure 356A with the schematic of the circuit is drawn with a box-like fashion. In the previous illustration, to draw the circuit, start with the voltage across the trace of the path of the current junction marked A with the junction current divided with the 3 path of where the stretch over the wire to show the 3 current path of the circuit would appear with the figure 356B. Shows a battery with a resistor 1, resistor 2, resistor 3, also drawn out like in parallel connections, resistor 1, resistor 2, resistor 3. With a circuit that may appear different with the two drawn, they actually represent the same circuit with the drawn. Then the figure of the familiar box-like structure that may be easy to work with. Figure of the 357A with the schematic with the circuit shown in the box-like figure-like structure may be misleading. The circuit that may result in reality series parallel circuit that was redrawn with the shown figure 357B with the drawing part with the B figure simpler representation of original circuit could be reduced to 2 resistors in parallel. Alright, this shows resistor 1 and resistor, and then it redrawn into a simple series, 2, 3, and 4. Redrawing complex circuit to show the complex circuit with redrawn clarification following step 358A. Alright, so 358A, shows resistor 1, resistor 2, 6, 7, and 8, and 9, and 10, and then that would be 6, 7, 8, and 9, and 10. 6, 8, and then then you have resistor 2 would be resistor 7 with its own, and then the resistor 2, 3, and 4, and then resistor 5 on the outside. So I think there's an error in this one though. This is actually supposed to be 9 and not 8. Note as you redraw the circuit, draw with a symbol black form of each time of the junction with a new branch created with the stretching and shrinking of the wire. Start with the negative term of the voltage, sort with the current flow with the resistor 1 junction, and divide with the 3 path with the label the junction, file with the 1 path with the current with the resistor 2 and the resistor 3 junction where current divide with the 2 more path with the functions. Label the B with the current through the 1 branch of the junction, go through G through R5 with the back that sort with the most with the direct path. Now you have to believe with the path of the current to show a source, return the last junction of the B with the flow of the current within the other branch with the conjunction. From this junction, current flow for the junction B with the resistor 4, and from the circuit all path of the junction B have been traced with the ones of the path of the junction A has been completed. You must now return the junction A to complete with the other 2 path of the junction A with the current flow of the resistor 7 back to the source. There are no additional branches on the path of the return of the junction A with the 3rd path of the junction with current flow of the resistor 6 and 8. And comes to the junction, label the junction C, one path of the current through a resistor 9 and source over the one other path of the current junction with the resistor 10 of the source. All junctions or circuits have been now been labeled the circuit junction, the redrawn with the figure 38C with as much of the Asia with the series parallel current redrawing circuit. What is the total equivalent resistance circuit shown in figure 359? Redraw the circuit and simplify. You have the equivalent resistance, compute the resistance total. All right, that would be that's question 34. When you're looking at the questions, effects on open and short circuit. The circuit chapters for the in terms of open and short circuit. The following deal with the effect of the circuit that open and short occur. The major difference between open and parallel circuit that open the series circuit is that the parallel circuit open would be necessary to disable the circuit. If the open condition occurred within the series of the portion of the circuit, there will be no current because there is no complete with the current flow. If then, on the other hand, the open current occurs parallel path of the sum of the current show of the flow in the circuit of the parallel branch for the open curve that effectively disable the total resistance of the circuit is increased with the total current decrease. To clarify, these figure 361 illustrate the series parallel circuit. The first effect of the opening in open in the series portion of the circuit will be examined in figure 361A with the show the normal circuit resistance total of the 40 ohm, then the amp the totals for 3 amp. The figure 361B is open shall be in the shown in the series portion of the circuit. There is no complete path of the current resistance. The circuit is considered infinite. All right, so resistor the total voltage is 120. You have resistor 1 would be at 20 ohms, and this would also be run from resistor 120 volt resistor and 20 ohms. You still have a resistor. This is a break-in short, or this is an open. A resistor ohms 100 125. Show the 120 volts resistor 1 ohm, resistor 2 100, resistor 25C. Notice the short has moved from resistor 1 to resistor 3 on the outside. Since they're on the outside, like there's 3 parallel circuits. Resistor 1 equation. Figure 31.6c is open shell between the parallel branch for 36. The resistor 3, the no path of the current through resistor 3. If in the current flows through resistor 1 and 2, since there is only one path of the current flow, the resistor 1 and resistor 2 is in series. Under these conditions, resistor total is 120 and total 1 amp. As you can see, when it opens a curve parallel branch, total circuit resistance increases, the total circuit the current decreases. The short circuit parallel network and effect similar with the short series circuit. General short will cover the increase of the current possibility of the component damage regardless of the type of Circuit involved to illustrate the point in Figure 362 show that the series parallel network in shorts and or developed in Figure 362A with the normal circuit shown with the resistor total is 40 ohms, and the so you'd have 145 ohms over 145 ohms. Uh, Total ampage for 3 amps. Show the resistor 2 and 3 ohms, 125 ohms. Notice that the resistor on would be 0 of the 20 ohms, 100 and 0 ohms. The series parallel with shorts, so original circuit, a short in resistor 1, short in this next serial resistor, parallel resistor 2 circuit. Alright, in Figure 362, the resistor 1 has been shorted. Resistor now has 0 ohms of the resistance. The total resistance of the circuit is now equal to the resistant parallel of the resistor 2 and resistor 3, the 20 ohms. The current, the circuit current is recorded at 6 amps. All the current goes to the parallel network through resistor 2 and 3. The increase of the current mode most likely damages the components. In Figure 362C, our resistor 3 is shorted, the resistor 3 is shorted, the circuit with the parallel resistor 2, the short circuit with the current resistor 2, effectively removing the resistor 2 from the circuit. The total circuit resistor is now equal to resistance 1 of 20 ohms. Alright, given the resistor 2 is 100 ohms and resistor 3 is 0 ohms. Alright, we're on part C. Resistor equation would be resistor 2 times resistor 3 would be 0 ohms over 0 ohms. That means the short is there's a short in the circuit here, so this would be 0, that you'd have 20 ohms, and then this one would be 125 ohms. Over divided by, it'd be 25,500 ohms over 125, whatever that would be. Total amount of circuits of the current of the R3 is short of the 6 amp of the current flow. The resistor would most likely damage enough that the only portion of the parallel network would be short. The entire parallel network is disabled. Open and shorts alike are for the current of the circuit the result of the overall chain, but the equivalent of the resistance of the scale of the undesirable effect of the part circuit to do with the corresponding chain with the total current flow. A short usually causes the components to fail when the circuit is not properly fused, but the other were protective of the failure may form when the burned out resistor damage short with the fire and circuit the components of the wiring. So you gotta have a fuse. These fuses and other circuit protection devices are installed with equipment serve to prevent damage of the coil with increase the current. These circuit protection devices are designed to open the current and increase the determinant value, but the circuit protection devices are connected with the series power and the circuit portion of the circuit device's protection. When the circuit protection device is open, current flows and see the circuit. The portion of the explanation of fuse of the other circuit protective device is present with the module 3, introducing the circuit protection and control measurement. Where they have the effect of the total resistance, total current with the circuit that opens curve of the A with the parallel branch and B in the series portion. With the effect of the total resistance and the total current of the circuit is shown in a curve of the part A with the parallel branch and B the series portion. If the branch and parallel network is short of the portion of the circuit of the flow through the remaining branches. Alright, voltage dividers. Most electronics and electrical and electronics equipped with the voltage various levels through the circuitry. One circuitry may require a 90 volt supply and another 150 volt supply, still another 180 volt supply. The voltage requirements could be supplied with 3 individual power sources. This method is expensive and requires a considerable amount of room. The most commonly method of supplying these voltages is to use a single voltage source or voltage and a voltage divider. But the voltage dividers are explained with a view that discussed earlier and concerning the voltage reference may be help. As you know, that some of the circuit is designed as some of the both positive and negative voltage. Perhaps now you wonder if the negative voltage has any less potential than the positive voltage. The answer is 100 volts is equal to 100 volts, with a negative whether it's negative or positive does not affect the feeling you get when you are shocked. Your voltage polarity is considered being positive and negative with respect to the reference point, usually ground in Figure 363 helps to illustrate. All right. This is 100 volts. There is resistors 1 through 4 would be and then A would be 0 volts because of the ground. B would be 25 volts, 50 volts, 75 volts, and E volts. This would show that the voltage polarities. Figure 36A shows the series of circuit of the voltage source of 100 volts with 4 ohms, which would be 200 divided by 4 with 100 with 1 to 1 amp resistance. The ground reference point with the connect with the one of the end of the resistor, one with the current in the circuit with the determined with the ohms low is a half an amp. So actually like what was it? 200 amps. 200 ohms voltage amperes equal to volts over the ohms, so you get a half an amp. As indicated with the schematic, the voltage measured for each of the point for the A to E, the 0 volts becomes more positive within 25 volts to value with positive 100 volts. In Figure 363, the ground reference point would have moved to point B. The current of the circuit is still flat, half of an amp. Each of the resistor stats still develops 25 volts. The total voltage developed in the circuit remained with 100 volts because the reference point has been changed with the total the voltage point A, the negative the 25 volts, point E, which is the positive of the 100 volts, but the Figure 360A, but it now has the voltage of the 75 volts. You can see the voltage of the point of the circuit depending on the three factors of the current, the resistor, the automatic value with the resistor, and the reference point of the circuit. Your typical voltage divider consists of the two or more resistors connected with the series across the source of the voltage. The source of the voltage is higher than the voltage developed at the voltage divider. The source of voltage address drop the successive step of the series resistor and any desired. So the ground has changed. So there would be resistor would be 50 ohms and negative 25 amps. Notice that it shifted itself down the 25 volts. Portion of the sources Figure 36.4 is issued to illustrate the development in simple voltage divider. The requirement of the voltage divider is to provide with the voltage of the 25 volts current with the 910 milliamp of the load and the source voltage is 100 volts. Figure 36.4a to provide with the current with the 25 volts available at point B. Load is connected between the point B with the ground. You might think that the load will be a supply with 25 volts. This is not true since the load connected between B and ground forms a parallel network load with the resistor. Load and resistor 1. Remember that the value of the resistance of the parallel network is always valued with the smallest resistor in the network. So you have resistor 1, 2, and 3 shown in the battery. Show the resistor 1, 2, and 3 as in simple voltage divider, dividing them up. The sense of the resistance network will not be less than 25 ohms. The voltage of the B would be less than 25 volts. This would not satisfy the requirement of the load. Determine the type of the resistor of the voltage divider of the rule of thumb of the current. And the divider resistor shows equally approximately 10% of the load current. The current load, the current which does the flow through each of the load devices is called the bleeder current. Given the information, the voltage divider can be designed with the following steps. Determine the load requirement available to the voltage source. You have 100 volts over the E25 volts load. And the amperage loading would be 915, 910 millivolts. The amperage load, the 900 milliamperes. Select the bleed current. The amp of the resistor 1, 10% of the ampere load, 910 millimeters, 91 milliamperes. Check calculate the bleeding resistance resistor 1 over the voltage of the resistor. Voltage of the resistor amperage over the resistor, and you have 274.73 ohms. The value of the resistor 1 may be found as 275 ohms, rounded. To calculate the current of the load plus the bleeder, the total amp of the load is 910 milliamperes plus the amperage of the resistor 1 and 91 milliamperes equals the total of the 1 amp rounded off. The calculated resistance of the divided resistor voltage resistor 2 is equal to the total the battery voltage minus resistor 1. They give these 75 volts at resistor 2. Resistor 2 is equal to the voltage of the resistor 2 over the amperage is equal to 75 ohms. The voltage divider circuit should not be drawn as shown in figure 364b. What are the information we know to determine the component value of the voltage divider? If the voltage divider is required to load the 400 milliamperes of the current, which should be the value of the believe of the current load over the question 50 required voltage of the 90 plus volts should be the value of the bleeder with the resistor. The source of the voltage of the voltage divider question 50 supply with 150 volts for the total current through the voltage divider. Alright, multiple load voltage dividers. Multiple load voltage dividers are shown in figure 365. The important point with the emphasize with the beat before you within 10% of the rule of thumb to calculate the bleeder current you must take 10% of the total load current. Alright, multiply the load voltage divider. So the total voltage between the positive and negative is 285 volts ES, resistor 1, resistor 4, and 3 different circuits, resistor 1, 2, and 3, and 4. You have 175, load 1 would be 90 volts, 10 milliamperes, load 1, load 2, 150 volts, milliamperes, load 2, 175 milliamperes, load 3, and you have the 285 volts. So, given the information figure 30, you can calculate the value of the resistor need with the voltage drop with the same step with the valve and the previous voltage drop dependence. Load 1 would be 90 volts over the 10 milliamperes, and load 2 would be 150 volts over 10 milliamperes. And the voltage of load 3 would be 175 volts at the amperage of 300 milliamperes. The total amperage is 285. Bleed current should be 10% of the total load current. The existence of the one resistor at 10% of the amperage load total. 10 milliamperes, so you have 10% of the 10 milliamperes times 10 milliamperes times 30 amperes is 5 milliamperes. At 10% of 50 amperes would be 5 milliamperes. Since the voltage across the 60R1 is equal to the voltage requirements of the load 1, Ohm's law can be used to calculate resistance 1. Value of the resistor 1. Resistor 1 is equal to the voltage of the resistor 1 over the resistor in milliamperes, so we have 90 volts over the 5 milliamperes or 18 kilo omega. The current resistor 2 the amp of the resistor 2 is equal to the current of the resistor 1 plus the current load of the resistor 1. So resistor 2 is equal to resistor 1 amp of the resistor 1 with the input amp amps of the resistor 1 5 milliamperes times 10 amps to 15 milliamperes. Voltage of the cross resistor 2 the voltage of the resistor 2 is equal to the difference between the voltage requirements for the load 1 and load 2. So voltage of the resistor 2 is equal to the voltage load of the resistor 2 and the voltage of load 1. For you got 60 volts in the ohms law. Now you solve the resistor 2 is 60 volts over 115 milliamperes is the amperage. Resistor 2 4 kilo ohms is resistant. 4 kilo omega is your ohms. The current resistor 3 the amperage of the resistor 3 with equal to the current of the resistor 2 apply for the current load of the load 2. The resistor 3 is equal to the resistor amp of the resistor 2 of the amp of the load 2. 15 milliamps 20 amps to 25 milliamperes. The resistor 3 is equal to 175 volts minus 150 volts is 25 volts. Okay, so almost can now be solved with the resistor 3. Resistor 3 show that the resistor 3 is equal to the voltage, the ohms of resistor 3 is equal to the voltage of the resistor 3 over the amp of the resistor 3, 25 with the diminished 1 kilo omega. Certain resistor 4 and amp of the resistor 4 with the current flow of the resistor 3 plus with the current flow of the load 3 is amp of the resistor 3 equal to the total circuit. So amps of resistor 4 with plus amps of the resistor 3 with the amp of the resistor 4 is 150 milliamp of the resistor 4. The voltage across the resistor 4 equal to the difference between the source of voltage of the requirement of the load 3. So you have 110 volts after 285 and 175 volts of it and equaled. That was the total voltage minus the load of 3, 110 volts. Solution: resistor 4 is equal to the voltage of resistor 4 over the amp of the resistor 4, 110 volts, 55 milliamperes, or 2 kilo megas. The calculation just been explained. The valuation of the resistor voltage dividers are resistor 1 18 kilo megas, resistor 2 at 14 kilo megas, resistor 3 1 kilo mega, then resistor 4 2 kilo megas. Alright, power in the voltage divider is an extremely important quantity of the power dissipated with the resistor of the voltage divider should be calculated to determine the power handling requirements of the resistor. Total power with the circuit needed to determine the power requirements of the source. The power circuit shown in figure 365 is calculated given the voltage of resistor 1 is 90 volts and the voltage of resistor 1 is also 5 milliamperes. So you have amps and voltage. So 90 volts is equivalent to the same as 5 milliamperes. So the power resistor of the resistor 3 and the amp of the resistor 1 is 90 volts plus 5 milliamperes. I believe they got that wrong. That should have been an I there. The power resistor is 0.45 watts. The power each of the resistor calculated with the resistor 1 when calculations are performed. The following results are obtained. Power resistor number 9 watts, power resistor 6.25 watts, and power resistor 4 0.5 watts. Calculate the power. The voltage loaded number 190 milliamperes, 1 amp load 10 milliamperes. So you get the power load is 90 volts times 10 milliamperes, 9 watts. The power should be each calculated for the load with the calculation performed. The following results: power load 2 would be 1.5 watts, power load 3 would be 5.25 watts. Total power is calculated. Some of the power consumed with the load with the power dissipated with the divided resistor of the total power and circuit with the 15.675 watts. The power used with the load with the divided resistor supplied with the source with the supply with the electrical power with the components supplied with the source. Since the power is produced with the voltage current with the power supplied with the source is equal to the source of the voltage multiplied by the total circuit current. The total voltage times the total amperage. The current figure 35 over the total power is the 285 volts over the times the total 555 milliamperes and you get the 15.65 milliwatts. Voltage divided with the positive and negative voltage requirement to make it with the load with the voltage divider required with both positive and negative. The positive and negative volts can be supplied with a simple source of the voltage connected with the ground reference between the two divided resistor. Each extent point with the circuit of the reference point and then play depending on the voltage required by the loads. For example, the voltage divider can be designed provided with the load voltage and congruent with the reload of the given source load of the voltage negative 25, the amp to 300 millimeters, load 2, the voltage is positive 50 and amp to 50 milliamperes. Load 3 is the 250 volts and amp to 100 milliamperes. The total voltage to be 350 volts. Circuit shown, the shown figure 36 with now the plate from the ground reference point. The values of the resistor 1, 2, and 1, 3, and 4 with the computed exactly what was done in the last example. The amp of the resistor 1 bleed current can be calculated as follows. So you have 310 volts, negative 25 volts, 3 and load. Then you have solution 1 amp of the resistor 1 of the 10% of the amperage load total. The amp of the resistor 10% of the 300 milliamperes is the amp of the resistor 1 at 300 milliamperes. Resistor 1 is equal to the voltage of resistor 1 over the amp of the resistor 1, 25 over 45 milliamperes with the 560 megas, 556 omega with the calculate the current resistor 2 with the Kirchhoff the current law. That means that 45 milliamperes of 300 milliamperes over the plus of the resistor gives you 195 milliamperes and resistors. Big equation. I feel like skipping this one. And practical application voltage dividers. The application practice computed with the value of the bleed resistor does not always come out even the value of the rule of thumb of the bleeder current is the only estimated value of the bleeder can resist the value of the load of the computed valve. The computed valve of the resistor is 510 ohm. The 500 ohm resistor can be used. Once the actual value of the bleeder resistor is selected, the bleeder current must be replaced with the voltage developer of the bleeder resistor must equal the voltage of the requirement of the load and parallel bleed resistor. The value of the remaining resistor voltage divider is computed with the current through the remaining resistor voltage. The current within the value must be provided required with the voltage current load, but the computed value of the divider resistor, not even the value of the series parallel network can be provided with required resistance. Example: the voltage divider is required to supply with the loads of the 190.5 volt source. The load 1 requires 45. Load 1 plus 45 volts and 210 milliamperes, and load 2 and requires 165 volts at 100 milliamperes. Calculate the breed current with the rule of thumb. Amp load 1 and 210, amp load 2 is 100 milliamperes, so you have the amp of the resistor 1 at 10% times 210 times 100 is 31 milliamperes. Is the voltage of the resistor 1 is 45 volts, and the times the voltage load number 1, the amps resistor is 31 milliamperes. Resistor 1 is equal to the ohms of resistor. Resistor 1 is equal to the voltage of the resistor 1 over the amp of the resistor 1 to give you 141,451.6 ohms. So this will be difficult to find the resistor 145.16 ohm. In practice, show if it resumes at 1500 ohms. If they calculate the actual bleeder current, the selected value of the resistor 1. The voltage of the resistor 1 is 45 watts, and the 45 volts of the amp of the resistor 1 is 1.5 kilowatts. The one resistor 1, the amp of the resistor 1, voltage of resistor 1 over the resistor, over resistor 1 equal to 45 over the 1. The resistance at 1 is 105.5 kilo ohms or 30 milliamperes. Use the value of the amp of the resistor 1 to calculate the resistance need of the next divider of the current resistance amp of the resistor number 2 the believe of the current parent of the aspect load 1 amp of the resistor 1 is 30 milliamperes. The amp of the resistor load 1 is 200 milliamperes. Solution: the amp of the resistor 2 is equal to the amps at resistor 1 and the load at 200 milliamperes, where they give you 240 milliamperes, and at resistor 4 the voltage of the cross of the resistor 2 and the voltage of resistor 3. Voltage of resistor 2 with the voltage of resistor 2 is equal to the difference of voltage requirement to the low of the 2 and 1 over the 120 volts. Calculate the value of the resistor 2. Given that the voltage 2 is 120 volts, the amp of the resistor is 240 milliamperes. The resistor 2 with the equal to the amp of 120 volts over the 200 milliamperes, but it gives you 500 ohmegas. The value of the final deserve of the resistor calculated with the amp of the resistor 3 with the amp of the amp of resistor 2 with the amp of the resistor 2 with the equal to amp of the load 2 that equals 340 milliamperes. And voltage of the amp 3 equals is voltage total minus the voltage load of 2 equal to 25.5 volts. Given the voltage of the resistor 3 is 25.5 volts and the amp of the resistor 3 is 340 milliamperes, the resistor number 3 is equal to 25.5 volts over 340 milliamperes, the 75 ohmegas. Or ohms. The 275 ohm resistor may not be easily obtainable. The network resistor of 75 ohms can be used in place for the resistor 3. Any combination of resistor 5 adding the 75 volt ohms could be used in place and then serve the development the required network. For example, the 37.5 ohm resistors. You could connect the series to get with the network with 75 ohms, 1 ohm, 50, 1 ohm, 25 resistor series, or 710 ohms and 1 5 ohm resistor. Parallel network constructed with the two 150 ohm resistors or 3 225 ohm resistors. If the parallel networks would be networks of 75 ohms. The network we use the example of the series parallel network using 3 50 ohm resistors. So with the information given, you shall be able to draw the voltage divided networks. The value of the various divided resistors have been selected. You can compute the power used with the resistor method. The previously explain the power used with each of the resistor known the wattage required with each of the resistor. Determine the physical side of the type of the need of the circuit shown in Figure 367. Figure 367 was a practical example of voltage dividers and then equivalent circuit techniques. Circuit solution have been studied up to the points that have been obtained mainly through the use of the formulas derived by the Ohm's law with any other field of the science of electricity as shared with a special shortcut of the methods on special circuits analysis of the Thevenin's theorem, which is used with the process of circuit reduction. Thevenin's equivalent circuit in Norton's theorem. Which reduction of the circuit with Norton's equivalent. Any other method is called loop analysis. This is Kirchhoff voltage law simultaneously solve the problem of the parallel branch of the circuit. The use of these methods be reserved, in which will have become some familiar with the methods covered in the part of this chapter. You want to explore them in special technique later in the career. Alright, electrical safety. Safety precautions may always be observed by the person working under electrical circuit equipment to avoid injury with electrical side. Detailed safety precautions contained in the Navy MAT and P51 safety precautions with the shore activity to Op Navy is 55119 Navy's precautions for the safe forces afloat. Danger shock from 100-volt AC electrical systems will recognize the operative of the personnel shown with a relatively low number of the report serious shock of the received them in the voltage of the display with the widespread. On the other hand, a number of fatalities have been reported due to the contact with low voltage circuit. Despite the unfairly widespread, totally unfound popular belief to the contrary. Low voltage circuits of 150 volts or below are very dangerous and cause death when the resistance of the body is lowered. Fundamental current rather than voltage is more measure of the shock of the intensity. The passage of every small current through the vital part of the human body can cause the death. The voltage necessary to produce the fatal current is dependent upon the resistance of the body, contact condition, the path of the body. For example, the example of 60 Hz alternating current is the path of the human body from hand to hand, the hand to foot. Current is gradually increased. It will cause the effect of about 1 milliampere. The shock can be felt about 10 milliamperes or 100 of the ampere of the shock with a sufficient intensity prevalent in the voluntary controlled muscles. About 100 milliamperes or 1/10 of an ampere. The shock is fatal lasts for about 1 second above the figures. The result of the numerous investigations are approximate because the individuals differ. The resistance of the electrical shock is the most important. Recognize that the resistance of the human body cannot be relied upon prevent to fatal shocks from 150 volts or less. Fatalities from voltages as low as 30 volts have been recorded. Tests have been shown body resistance to unfavorable conditions may be as low as 300 ohms, possible as low as 100 ohms from the top temple to temple, or if the skin is broken. Conditions aboard ship: the champ of receiving the electrical shock of the board. The ship of the body would likely to be contacted with metal ship of the body with resistance lower, peak out of the perspiration, damp clothing. Extra care and awareness electrical hazards aboard the ship that are needed. The short circuit that can cover the accidental plate for the dropping the metal tool, rule, flashlight case, or any other conducting article that you energize the alarm. The arc of the fire of the will result with the eventually relatively low voltage circuit that may extend to the damage of the equipment, serious injury to personnel. Since ship the surface power with the distribution are designed to be ungrounded, many personnel believe it's safe to touch one conductor, so since no electrical current will flow. There's no true, since the distribution system is not totally isolated with the whole of the ship. If one conductor is ungrounded, electrical system is touched with the body in contact with the whole of the ship. The other metal equipment, the enclosure with the fatal current, electrical current may pass through the body. All live electrical circuits shall be treated with this potential hazard at all times. Danger signals. Personnel should constantly be alert with any of the circuit sign with the indicator of the malfunction of the electrical equipment. Beside with the many more obvious visual sign of the reaction, other sensitive such as the hearing, the smell, and the touch, but make them aware of possible electrical malfunctions. Example of the signs which make the alert with the air are fire, smoke, sparks, and arcing, and an unusual sign with electrical motor. Afraid of damaged cords, plugs, or receptacle plugs and cords that which feel warm to the touch, slightly shock available, felt with a handling equipment, usually hot running electrical motor to other electrical equipment, in order to bring overheated insulation electrical equipment which have either failed to operate with the regular electrical equipment. If the excessive vibrations also indicate the malfunction. When the above signals are not noted, reported immediately to the qualified technician. Do not delay. Do not operate faulty equipment. Above all, do not attempt to make any repairs to yourself that are not qualified to do so. Stand clear with the suspected hazard of the instruct that otherwise do likewise. Warning sign: they have been played for your protection. Disregarded to invite the personal injury with the possible damage of the equipment. Switch them receptacles with the temporary warning and tag with the indicate the warning work is being performed and not to be touched. Work near the electrical equipment. Working near electrical equipment when working with the performer immediately visiting the electrical equipment. Check with the technicians responsible for the maintenance of the equipment so you can avoid potential hazards if you may not immediately aware. Authorized personnel because of the damage of the fire and the damage of the equipment. Injury of the personnel. All repair maintenance of the electrical equipment should be done on the authorized personnel. Keep your hands off all equipment when you have not been specifically authorized to handle. Particularly stay clear of the electrical equipment open with the inspection, the testing, and the servicing. Circuit breakers. Circuit breaker fuse to cover all the fuse box, the junction boxes, which box, the wiring, accessory that should be closed, and the name of the cover. Do not cover those with the miss should be reported to the technical responsible for the maintenance. Failure to do so result in injury, personal damage, equipment, the event of the accidental contact made with the exposed live circuits. Electrical fires. Carbon dioxide, CO2, the G of the fires, electrical firing, fighting electrical fires. No conductive thereof for the safety of the term electrical safety. Also offers likelihood of the damage of equipment. However, the discharge of the horn CO2 extinguisher is allowed the accidental touch of the energized circuit. The horn may transmit the shock of the personal handle to the extinguisher. In very quantity of which cover the CO2, the variable extinguisher agent will also make the dangerous life of the replace with the oxygen air. The extent of the combustion cannot be sustained. Respiration cannot be sustained. Exposure of the person to an atmosphere of high concentration of CO2 will cause suffocation. Our first aid for electrical shock. A person who stopped breathing, not necessarily dead, but in immediate danger of life, is ill, dependent upon the oxygen breath into the lungs that can be carried with the blood to every blood body cell. Since the cells cannot store oxygen, since the blood can hold only a limited amount, then only in a short time the death will surely result when the continued lack of the breathing. However, the heart may continue to beat some of the time after the breathing of the stop of the blood, but the may be still circulated to the blood cells. Since the blood will a short time continue a small supply of oxygen, body cells will not die immediately. A few minutes there is some chance that the person's life may be saved. The process in which a person who's been stopped breathing can be saved is artificial ventilation and respiration. The purpose of the artificial ventilation is to force the air out of the lungs into the lungs with a rhythmic alteration until the normal natural breathing is reestablished. The artificial ventilation should be given only when the natural breathing is stopped. It should not be given to any person without breathing naturally. You should not assume that the individual who is unconscious due to the electrical shock has stopped breathing too. Tell him something to suffer. Tell if something is suffering from the electrical shock with a breathing. Place your hand on the person's side at the level of the lowest ribs. If the victim is breathing, you will be able to feel the movement. Remember, do not give the artificial ventilation to a person that is not breathing naturally. Records show that 7 out of 10 victims of electrical shock with revived the artificial respiration stored in less than 3 minutes. After 3 minutes, chance of the revival decreases rapidly. Once it has been determined the breathing is stopped with the person near the victim should be start the artificial respiratory ventilation without delay, sending others in the resistance of the medical aid. The only logical possible delay that requires the free of the victim with the contact with electricity is in the quickest and safest way. This step, while is mostly taken quickly, must be done with great care, with otherwise may do the two victims instead. And keep the portable electrical tools light and applying with equipment and portable outlet extensions. It should be done turning off the supply switch, removing the plug from the receptacle. If the switch of the receptacle cannot be quickly located, the suspected electrical device may be pulled free of the victim. Other person arriving in the scene must be clearly warned not to touch the suspected equipment until de-energized. Aid should be enlisted to unplug the device as soon as possible. The injured person should be pulled free of the contact stationary equipment such as the bus. For equipment contact cannot be quickly de-energized. The conservation military operation of unit survival prevent immediate shutdown of the circuits. This can be done quickly, safely, and carefully applying the following procedure. Protect yourself with the insulating materials, dry board, belt, and clothing available, non-conductive bent metal to free the victim of electrical contact. Do not touch with the victim until the source of electricity has been removed. Once the victim has removed the electrical source, it should be determined if the person is breathing and the person is not breathing. The method of the artificial ventilation is used. Sometimes victims of electrical shock suffer the cardiac arrest, heart stoppage as well. With the loss of the breathing of artificial ventilation is not enough to indicate that the heart stopped. The technique of the no as cardiopulmonary resuscitation has been developed to provide aid of the person who has been stopped breathing and suffer cardiac arrest. Before you most likely will be working in the field with electricity. Risk of electrical shock is higher than most of the Navy occupations. You should at your earliest opportunity learn the technique of the CPR. The CPR relatively easy to taught in the course of the American Red Cross, some of the Navy medical departments, and standard first aid training course, Navy 12801. Summary. Alright, and that concludes chapter 3, and then we'll come back and read the summaries. And skip the appendixes and the glossary and index.